Welcome guys, I'm Gio here, hope you're having a great day, and this is a new series on the channel. I'll be discussing programming interview questions, and the first video is dedicated to a problem from a Google interview. I'll be showing you the problem, then we will talk about some intuition behind the solution, then I'm going to show you implementation, and I'm going to break down all the parts of the solution so everything is clear, and finally we will talk about some time and space complexity and summarize all the points. All the necessary links will be provided in the description box below. So let's jump into the problem. This problem is from binarysearch.com. You can check the exact link for this problem in the description box below. So basically, in this problem, we are given a matrix of zeros and ones. Zeros represent an empty space and 1 represents a communication tower. Also, we have some conditions there. Towers can communicate with each other, A and B tower, if they are on same row or on the same column. Also, if tower A can talk to tower B and B can talk to C, they A and C also can talk to each other through B. So we have some groups of communication towers that are connected with each other. We are asked to return the number of groups of communication towers that can communicate with each other. That's the problem. And then we have some constraints there. Before we move on to solution, let's check some examples. Here answer is 2 because we have exactly 2 groups. Towers within these groups can communicate with each other. We have another example. And here the answer is 3 because all of these towers are independent and none of them can communicate with each other, and these single towers form the group of 1. So we have this 3. Before I move on to solution, I strongly encourage you to check the problem link down below and try it yourself, give it a try, and then come back here, maybe compare solution, or if you get stuck, then you can check this and it will be much more useful. Let's get the intuition behind the solution first and then move on to the exact implementation. So whenever there is a talk about the groups and connections and networks and matrices and such, I think in terms of the graphs. And here if we imagine that somehow we have a graph of these connections, then counting the groups of the communication towers that are connected together is very trivial. We can use DFS or depth first search and just count the number of groups. Now if that is the case, the next question is, can we build a graph in a reasonable amount of time so then we can run DFS on? And the answer is yes, we can build the graph, and this is the bulk of this solution. So let's discuss this next. How can we build a graph? In this example we have 3 ones and they are within the same group. Now we have to make a key observation here. It is not necessary to make all the connections between the same group. Yeah, if we take a look at this one, we can connect it to the one on the same row. It's not necessary to make all the other connections, even though these can connect to all the other ones, the one in the upper corner. And if we make this one connection, then the group is connected together and then we can run DFS. We don't have to make all the connections within the same group. That's the point. This will allow us to build a graph in a reasonable amount of time just by iterating over the given matrix once. We have to iterate over the matrix once, and we obviously are going to ignore the zeros, but whenever we encounter 1, we have to ask the question, is there anything on the same row or on the same column that we have encountered before we got to this point? In this case, answer is no, because this is the first entry in the matrix and we do nothing. But we mark that on the 0th column and on the 0 row there is 1, that there is a tower there. And we'll check exactly how we do this in the implementation section. And then we are done with this point because it's not connected to anything yet. So we continue our iteration, we ignore the zeros, and then comes this one. Here again we ask the question, Was there anything on the same row or on the same column before? And the answer in this case is yes. On the column with index 0, we have encountered 1. So we make connection with that 1 on the same column. And then we continue. The last one in this matrix is this. And here again, we ask the same question. And is there anything on the same row or on the same column that we have encountered before? The answer is yes. And we connect it to the one that was on the same row. So we are done with it. And that way we have created the group and we have built the connections, and then we can run DFS and calculate all the groups. So how exactly is it done? Well, this is the solution here. I'm going to show you different parts so it is less confusing, and I'll walk you through all the parts. So when the test cases will be run, we are expected to return the number. Again, this is the TypeScript code, so it will be easier for you guys to understand. And we have two variables here. In the beginning, we have a graph and visited. They are both maps. And the graph is the key value pairs of numbers and array of numbers. And keys represent here the nodes. And the arrays represent the neighbors of the given row. So we can iterate over its neighbors if it's necessary. And also we have a visited. It is just a number in Boolean. Again, numbers represent, or keys represent here the nodes, graph nodes. And we need to use this to check if we have explored the given node or not. As you see, some parts are missing from this code, and that is intentional. I want to focus on different areas first. In between this and the final lines, we have the graph generation. It's a bit complex code, so I will discuss it separately. And then we have DFS implementation. But the final part here to get the final solution is this. We have the answer variable. And we basically iterate over every node that we have, or over every tower. And if we have not visited the tower yet, it means that we have discovered the new group, and we just run the DFS from there. So initially we start from 0, and we always explore the 0 and increase the answer. So we have one group. When the DFS is done, we continue the loop. And if we encounter any node that is not visited, it means that it was not part of any previous group that we have explored. So we increase the answer. And finally, when all the nodes are exhausted, we will get our answer. Let's check the DFS implementation now. It is very simple. It is expecting the graph, visited, and node, the current node that we are exploring. And once we get inside, we immediately say that this node is already explored. So we don't get in there again and get an infinite loop. And then what we do is that we iterate over the neighbors for the given node. That's why we have a graph, and we can get access to the neighbors very quickly. And then for every child node or neighbor node, we check if it is not visited. Then we want to run DFS from the given node. Well, if it is visited, then we don't care because it is already explored. Let's move on to the largest part of the solution, where we generate the actual graph. We have two additional maps here, rows and calls. We use that to check if we have encountered anything on a given row or column before. We also have the current point index or current tower index that will be generated when we discover the one. Then we iterate over the matrix or the input once. This is double for each, and obviously we're going to ignore the zeros, and when we encounter the 1, then we start building the process of the graph. So first of all, we need to generate a new index for our new point, and in this case we just take the graph size. Initially it will be 0, so the index for the first point will be 0, and so on. We can create an additional variable for this, but graph size will be enough since it's already there. Then we initialize this new node, and in the graph we set that it has no neighbors at this point. We also say that it has not been visited yet. That's why we have these two calls. Now comes the connection building part. And first we ask if there was something on the given row before, if we have encountered something. And if that is the case, then we build this connection within two towers, within two nodes. The next, we do the same thing. We ask the question, have we encountered anything on the given column before? And if not, then we ignore this. And if we have encountered something, then we will build this connection. And finally, when we are done with all this relationship building between the towers, we say that on the given row and on the given column, we have encountered this given node, which is represented by current point index. After we are done with these loops, we have graph, and then we can run DFS, and you know already from there. So I will have the link in the description below for the complete solution, so you get the source code and check that for yourself. Now let's move on to the complexity of this solution. Let's start with the space complexity. We have rows and columns here, and they are the size of the dimensions of the matrix. We also have visited, and in the worst case, every element in the matrix is a tower, so we need a space for that. And then we have a graph, and in the worst case, we need a space for every element in the matrix, if every element is a tower. And also every node in the graph will have at most 4 neighbors, so that's the space complexity. Let's check the time complexity. We have this double loop here to iterate over the matrix and build the graph. Then we have DFS, and usually time complexity of DFS is number of nodes plus number of edges. And in the worst case, all the elements in the matrix are the nodes, are the ones, the towers. And we can say that, further simplify that complexity. And then we can ignore constant term here too, and also the term with the lower time complexity. So we get this. And this is it. We have space complexity and time complexity, and it is acceptable. You can check that for yourself. As I've said before, link to the exact problem on binarysearch.com will be there in the description box. Also link to my GitHub page for this exact source code of my solution, and you can check that as well. Let me know if you have any questions or you have any problems that you want me to discuss and make the videos on. Hope you enjoyed it. Click the like button, subscribe, and share it with your friends.